In this video, I'm going to go through OCR AS-level Chemistry. This is paper 2. This is the 2018 paper, and I'm going to do the second half of the paper. I've already done the first half in an earlier video. Okay. Right, so the first one is about organic synthesis. Bromobutane. It's got a boiling point of 102 degrees C. The student prepares bromobutane by reacting butanol with conch sulfuric and sodium bromide and makes 1 bromobutane there. Okay, now the student obtains a reaction mixture containing an organic layer, and that's 1.27, which is more dense than the aqueous layer. So the organic layer containing the product, the bromobutane, will be the bottom layer, and that's the one to keep. Okay. Right, so it says here, the student boils the mixture for 1 hour. Draw a labeled diagram to show how you safely set up apparatus for the preparation. Now, you can't boil, if you boiled butanol for an hour, it's quite volatile, as is the bromobutane, and they would both just evaporate and you'd end up with nothing left. So you have to use reflux. Okay, so this is the diagram they want. They want us to show a diagram heating with reflux. So let's draw that. So we have the condenser in the vertical position, like that. Okay, so you'd label that condenser, and then that would be connected. Here's a join. They like you to draw these joins sometimes, I think, rather than just one continuous piece. And a round bottom flask or a pear-shaped flask, it doesn't really matter. Okay, that's going to be with the, that's going to have the bromo, that's going to have the reagents in there. So your butanol and the conch sulfuric acid and so forth. You would also use some anti-bumping granules there, so that it boils nice and gently. You'd heat it there. Okay, the water should go in at the bottom of the condenser and should come out at the top so that it fills up the entire jacket, and you should label that. And pretty importantly, no stopper in the top there. Okay, you shouldn't, when you do reflux, you should not put a stopper in and build a pressure up in it. That's not safe. Okay, so that is the apparatus. And then we've got to outline a method how to obtain a pure sample of 1 bromobutane from the reaction mixture. Okay, so you get a when the reaction is finished, you'll end up with 2 layers, and the bottom layer is the heavy one, the one we want because of the density. So you're going to put that in a separating funnel. So here's a separating funnel of various different shapes, but importantly, they all have a tap at the end there. And there is your 2 layers. This is the aqueous layer, and this is the bromobutane that you want. Okay, now that bromobutane is going to be have a lot of contamination in it. It will have maybe a bit of butanol in there, a bit of dissolved sulfuric acid and various other things. So you're going to wash it. So what you do is you wash it with either distilled water or better saturated NaCl solution. So you put in 50 centimeters cubed of that, put a stopper in the top, shake it up, so all the water soluble things like the butanol will go into the aqueous layer and the sulfuric acid will go in the aqueous layer, and then you release, you take the stopper out and you run off the lower layer. So you keep the lower layer. Now you can wash it twice with the, I'd wash it ×2 with sodium chloride solution. And finally, then you want to wash it with saturated calcium chloride solution. And the reason for doing that is to that will remove the last few traces of water, which might be dissolved in the bromobutane. And then you, once again, you keep the lower layer. And then the final step to get it really dry is you should add some solid calcium chloride. So put your product into a conical flask or something with a bung in it so it doesn't evaporate. There's your bromobutane. And you should add a little bit of calcium chloride anhydrous, solid. And that will react with the water, any water that's remaining in the bromobutane. The bromobutane then can just be decanted off from the solid calcium chloride left over. Okay, so that should be enough for you for 6 marks there. Right, the student used, okay, this is going to percentage yield sort of thing, okay, they used 0.15 moles of butanol, and you've got a 61.4% percentage yield, so you've got to calculate the mass obtained. Okay, so let's just write down the equation. We've got butanol, which is C4H9OH. So 1 mole of butanol gives you 1 mole of bromobutane, C4H9Br. So let's just work out the MRs of those two things. So the MR of butanol is 74, the molar mass. So the molar mass of this one is 136.9. Now it tells us we start off with 0.15 moles of butanol. Right, now if we've got 100% yield, which it doesn't, we wouldn't get 100% yield, we'll get, because 1 mole of that gives us 1 mole of the product, we get 0.15 moles of product. Now let's see how much would that, what would be the mass of that. So mass is equal to mass of the product equal to the moles multiplied by the MR. So that's 0.15 multiplied by 136.9. That gives us 12.6 grams. A minute, it doesn't. That'll give us 20 odd grams or something like that. Let's see, 136.9 multiplied by 0.15. 20.535 grams. Okay, now we don't get 100% yield, we only get a 61.4% yield, so the mass obtained is going to be 20.535 multiplied by 64.1 over 100. That gives us 13. That gives us 13.16 grams. Let me just check that. Sorry, it doesn't. 20.535 times 0.614 gives us 12.6 grams. Okay, 12.608 grams. Now it gives us says the 3 significant figures, so we should give our answer as 12.6 grams. Okay, so here is about rate of reaction. So to investigate the rate of reaction of 1 bromobutane with aqueous hydroxide ions, and they measure the graph shows how a hydroxide ion concentration changes during the reaction. Okay, so it's falling. You can see at the start of the reaction, it's falling quite steeply as the rate's quite fast, and then it's falling much more slowly at the end because all the reactants have been used up and the rate of reaction is quite slow. So in that graph there, the rate is equal to the negative gradient of the line, okay? Right, use the graph to calculate the rate of reaction at 30 minutes. So what you've got to do is, like, there's 30 minutes there. You've got to draw a tangent to that point. So drawing that green line is a tangent. And we need to find out the gradient of the tangent. So the gradient is equal to the change in y divided by the change in x. Here's the change in y, this yellow line here. So delta y, we can see, well, it's 0 minus, and I think that's about 0.18 up there. So delta y is equal to minus 0.18. And delta x, I'm doing green here, changing the x. Well, I think that is more or less 75 minutes, isn't it? So 75 minus 0 is equal to 75. So our gradient then is equal to 0.18 minus 0.18 over 75. That gives us 2.40 times 10 to the minus 3. Okay, that is the rate of reaction. Okay, so we'll leave it to that, and we've got to think, well, that's the gradient is minus that, so the rate is going to be the positive, that positive value, 2.40 times 10 to the minus 3, and the units, well, the change in y, that's mole per decimeter cubed, and the change in x, that's minutes, so it's mole per decimeter cubed per minute, and that's what it tells us to work out the. Okay, so that is our answer, 2.40 times 10 to the minus 3. Oops. Okay. Right, so now this is an organic chemistry synthesis. Okay, let's have a look at this one. So we've got compound C. Okay, the first question, it says, give the systematic name of compound D. Okay, so compound D, we've got 2 carbons there. I'm going to call that number 2 and that number 1. I think I'll label it that way because then you're going to have more things on the lower carbons. So you'll end up with lower numbers in the name, which is what the correct way of doing it. Right, so it's going to be ethane. And what have we got attached to it? We've got 1,1-dichloro, and we have got 1,2-dibromo. Now they should go in alphabetical order, so I think the correct name is 1,2-dibromo, 1,1-dichloro ethane. Okay. Yeah, if you labeled it the other way around, then of course all those numbers there would be, that'd still be 1, 2, but that would be 2, 2, and that wouldn't be right because you want to have the smallest numbers possible. Right, so that's that naming done. Outline the mechanism for reaction 2. Well, what's happening in reaction 2, we are, see what we're doing, we are sticking on a bromine on that carbon and a bromine on that carbon. We've got rid of the double bond. So it is electrophilic addition by Br2 molecule. So let's draw the mechanism for that. Right. So here is our starting material. And we've got bromine. Now, bromine doesn't have a dipermanent dipole, but you will get an induced dipole. As the bromine approaches the double bond there, which has got a high electron density, it's going to repel the electrons. The electrons are all going to move down that end of the molecule. So that's going to make this bromine delta positive, delta negative. And this one delta positive. The first step in the mechanism is for a pair of electrons to, the pi electrons to move onto the bromine. And then for this bond to break, the pair of electrons there goes onto that bromine. Okay, so we're going to end up with a carbocation intermediate. Now the bromine could stick to either of those carbons, and I think the mark scheme will allow you to have either, but I think the more stable carbocation will be if it sticks onto that carbon there. So I'll draw that. The bromine goes on there. H and a positive charge there. This is the carbocation, and of course there's a bromide ion left over, and that bromide ion is going to go like that and form a bond to that carbon. So the final product is and you've got that there. Okay, so that is the mechanism for that reaction. Right, compound C forms an addition polymer E. Right, a balanced equation for this reaction. Okay, so show displayed for me. Right, we've got compound C there. So what's going to happen, remember, is I'll just draw this and then I'll rub it out. Is if you have two of those next to each other, you break the double bond and they form a new bond there. Okay, and so on. So let's draw that. So we're going to have this as a repeating unit. Okay, I draw a bracket around that. Now it does say a balanced equation, so we need to put an N in front of that. You've got N monomers, and that means you're going to get N repeating units in the polymer. Put the N there outside the bracket. Okay, that is our that's the equation for the formation of the polymer. Okay, state one advantage and one disadvantage of using combustion as a method for to getting rid of polymer E. Well, the advantage of burning plastics to get rid of them is that it's cheap, and you can use it to generate electricity as well, or use it as a fuel. The disadvantage is because this one contains chlorine, it means that you're going to get, you will also, when you burn it, you'll get HCl, and HCl, of course, are acidic fumes, and you need to dispose, you can't release that into the environment. Okay. Okay, so I think move on to the final question, question 7 now, which is a big structure determination question. Okay, so here you can see an infrared spectrum coming up. Right, compound F is a trans stereoisomer, so that means it must contain a carbon-carbon double bond, and that will probably be useful to us later on to know that. It's useful in organic synthesis. The results of elemental and spectral analysis compound F are shown below. Right, so let's first of all, before we look at the spectra, let us work out the empirical formula of this compound. So I'll just move over here. So what we've got, so that means we're going to have 68.6 grams of carbon in 100 grams. We're going to have 8.6 grams of hydrogen in 100 grams, and we're going to have 22.8 grams of oxygen in 100 grams. We need to work out the moles of those, not the mass. So the mass, the moles we work out by moles equal to mass over the AR, the atomic mass. So that's going to be 68.6 over 12, 8.6 over 1 for hydrogen, and 22.8 over 16 for oxygen. That gives us 5.71 for that one, 5.71 moles of carbon, 8.6 moles of hydrogen, obviously, and for that one, 22.8, 16. That gives us 1.45 moles of oxygen. Right, now to simplify this ratio of moles, what we do is divide by the smallest number. So we're going to divide by, the smallest number is 1.425. So let's do that over 1.425. And okay. So if we do that, 5.71 divided by 1.425. That gives us 4. 8.6 divided by 1.425, that is going to give us 6. And the oxygen, of course, is going to be 1. So the empirical formula then is C4H6O. Now we need, this is empirical. So first, what we're going to do is we're going to look at the mass spec to see if it's a multiple of that. Because what is the molecular formula? Is it C4H6O, or is it C8H12O2? Right. So what would be the MR of that? 4 times, if it was just one of those, 4 times 12 is 48, plus 6 is 54, plus 16 is going to give us an MR of 70. Now let's have a look at the mass spectrum to see if that is the parent ion. Let's go over here, the mass spectrum we've got here. Yeah, and the biggest peak we've got, sorry, the peak furthest to the right is that one at 70. So yeah, we can say the molecular formula is also C4H6O. Now before we look at the infrared spectra, I just want to talk about, this is very useful to look at this ratio of carbons to hydrogens. Now, if a molecule is saturated, no double bonds, it's CnH2n plus 2. Now, every time you have a double bond, you're going to lose 2 hydrogens. So, if it had one double bond, it would be C4H8. But it's not C4H8, it's C4H6. So that means that has our molecule has got 2 double bonds in it. Now we don't know whether they are carbon-carbon double bonds or carbon-oxygen double bonds. But they sort of gave the game away a little bit in the thing, because they said it can form stereoisomers. So that means we do know we've got a CC double bond in there. Right, now you've only got 4 carbons. So I suppose you could just about have, there could be 2 carbon-carbon double bonds, but I think there's probably a carbon-oxygen double bond in there, and we're going to look for that in the infrared spectrum. Okay. Also, if it's got a carbon-oxygen double bond, that means the oxygen is being used up there. That means there's no alcohol group, no OH group. And alcohol groups, you probably remember, are very easy to spot in an infrared spectrum. So let's have a look at the infrared spectrum and see which functional groups we've got in there now. Okay, so here's our infrared spectrum. Right, we can see there's definitely no alcohol there, because an alcohol, if you have an alcohol, where we go, about 3,200, somewhere like that, you end up with a really deep peak. Okay, and it's next to which is the carbon hydrogen peak. They're carbon hydrogens, which are not very useful because everything has a. So we said there's no alcohol in this molecule. There's no OH. That's part of our. We'll write that down in our answer. There's no OH because there's no peak in that region there. Right. What were we interested in looking for? Well, we're interested in looking for a carbon-carbon double bond. And it tells us it's got one alkene. It says 1620 to 1680. Well, I think that is that. See the little peak there, this one. All right, that is the CC double bond. And very close to that, you've got a C double bond O, carbonyl group, C double bond O. And that's just slightly higher, okay, slightly higher range. And that's that. I'll do that in green. That's that one there. So what has the infrared told us? It's told, of course, all this stuff here is that's all the fingerprint region, which is not very useful to us. Okay, so what it's told us, there's no OH, there's a CC bond, and there's a carbonyl bond. and we know the formula is C4H6O. Now we could suggest several different things with that. We're not quite we're not quite sure exactly what it is just yet. Okay, but they give us a bit more information in the mass spec. Okay, so what do they tell us here? They say in the mass spectrum, the peak with the greatest relative intensity is caused by the loss of a functional group from compound F. Okay, so here, look, this is the one here. What's the MZ value for that? That is 41, isn't it? Okay, that's 41. Okay, so they're telling us then that we've got the parent compound, which weighs 70. Okay, that fragments to give a fraction, something which weighs 41. Okay, and plus something else which has got to add up to 70, so it must be 29. And they also tell us that this is a functional group. Right, so what functional group have we got in there? Well, we know we've got a carbonyl, so I think you're going to find that that 29 is an aldehyde. Okay, does that weigh 29? So 12 for the carbon plus 16 plus 1, that does weigh 29. So we know from that little bit of information that we know that our compound contains an aldehyde group. So with all that, put all that information together, then what we're going to say is our final structure. We know we have got an aldehyde group. Now we know we have got a double carbon-carbon double bond as well. Now the double bond could go there, okay, but it can't go there, because if you do that, you can see, because you've got two hydrogens there, that means this compound can't show EZ isomerism, because these two groups are the same. So that can't be it. So the double bond can't go on the end one then. That means the only place the double bond can go is, we can't go there because that carbon's forming too many bonds. It's got to go there. And that would then show, that molecule would show EZ isomerism. So we're going to put there what we're going to have. We're going to have CH3. Okay. And you can, that molecule can show EZ isomerism if I draw the angle a bit better around that. I'm going to change that angle a bit. So more, so there's the carboxylic acid group, and there's the hydrogen, and just change these angles here to make it. So that's a hydrogen and that's a methyl. That's our molecule. That will show EZ isomerism, because look, you can either have the, in that case, I've actually drawn the E form there because that's the high priority one, isn't it? And that's the high priority one. Or you could have them swap around to give the Z form. So that is the only possible thing that it can be with all that information. Okay, so that is the end of that question, or the end of that question and the end of the paper.